Going to carry on with halogenoalkanes from yesterday, also referred to as haloalkanes. So yeah, I'm going to do a really quick recap of what we did yesterday and then go on to something called nucleophilic substitution reactions. So we looked at free radicals yesterday. So we looked at what a haloalkane is yesterday. So we said basically a haloalkane, a halogenoalkane, has a functional group where called CX. So basically X is our halogen, which could be fluorine, chlorine, bromine, iodine, and it's attached to an alkane. And our halogen is attached to an aliphatic skeleton, which has an alkyl group on it. And we said haloalkanes can either be primary, secondary, or tertiary, depending on how many other R groups, alkyl groups, are attached to that carbon that the halogen is attached to. We had a look at naming them. So for example, we're using our same prefixes as before, but we're now adding on the position for where the carbons are and saying how many of each halogen we have. We also said structural isomerism is really possible when we're making synthesizing haloalkanes. And these different structures are possible due to different positions for the halogen and the branching of the carbon chain. So here's basically formulae. We would have exactly the same. We have exactly the same atoms in all four of these molecules, but they're all four isomers because we've got different positions of the halogens on them, and we've also got some branching occurring. So we know isomers are highly likely. It's what causes a lot of issues when we're synthesizing halogenoalkanes, because actually lots of the isomers we don't want. We often just want one particular, and we make a lot of them, which is obviously not great for yield. But it's also not great because they're actually really hard to separate. They're really actually hard to separate from each other. So we don't like that either. Physical properties, we said the boiling point of halogenoalkanes increases with molecular size. That's due to those van der Waals forces inside them. And obviously, as we know, if we have any branching, our boiling point is going to be lower because those intermolecular forces are less. So the more branching we have, the lower those intermolecular forces are, which means the boiling point can be lower because it takes less energy to break those bonds. And also haloalkanes are soluble in organic solvents, but they are insoluble in water. And this is what we're going to look at today, nucleophilic substitution. So here we go. So the carbon halogen bond in halogenoalkanes, so you often see it drawn like this. You'll have a carbon and it'll be bonded to, we'll do it as X because that's how we normally do it. So we just erase that. It's polar, and that's because all our halogens are more electronegative than our carbon. So they're going to have a slightly negative charge and a slight positive, and they're polar bonds. So that lone pair of electrons are more attracted to the halogen. So we get this polar bond. So this is how we draw this carbon halogen bond in our halogenoalkanes. So it doesn't matter which halogen it is, they're all more electronegative than carbon. The polar bonds mean that the carbon atom has a small positive charge and it attracts substances with a lone pair of electrons. And that's basically because, like I said, those electrons that we've got here that are shared on the covalent bond are closer to the halogen, which is what causes that polarity to occur as well. So the polar bonds mean that the carbon atom has that small positive charge. And that small positive charge, because is able to attract substances that have a lone pair of electrons, because basically whilst they don't have an empty outer shell, because they're slightly positive, they're reacting in a way where it sort of almost is, because those lone pair of that pair of electrons that we share covalently are more towards the halogens. So these substances that they attract are called nucleophiles. And nucleophile means nucleus loving, so positive charge loving. So some examples of nucleophiles are ammonia, cyanide, and hydroxide. So what we're going to do is we're going to look at how we do nucleophilic substitution reactions, and then we're going to actually look at them specifically with ammonia, cyanide, and hydroxide. So nucleophiles, whilst we were saying obviously ammonia, cyanide, and hydroxide are all nucleophiles, and we always show nucleophiles with that lone pair of electrons next to them. While they're all nucleophiles, when we talk about nucleophiles as a general, could include any of those three or any others, we use this. I don't want to do that. We use Nu for Nu negative as a general shorthand for nucleophiles. And what they do is they attack the carbon of the carbon halogen bond, so that CX bond here. So they attack that. And because the electron pair on the nucleophile is attracted towards the small positive charge on the carbon. So here we go. Here's our halogenoalkane. We've got our halogen over here with its slightly negative charge, and we've got our carbon there with its slightly positive charge. The nucleophile is going to come in and it is going to attack that carbon here. So it's going to come in and attack that carbon. So what happens, and what's really important, is you look at how these arrows are being drawn. So if I drew it on my cell, I would draw it on as a full-headed arrow, curly arrow, full head. Yesterday, we were drawing half-headed arrows like this because we were talking about free radical substitution. So we were splitting those lone pairs. So they were half-headed arrows rather than a full head. Today, because we're talking about moving whole lone pairs, we use a full-headed arrow. So here we go. So the electrons in the carbon halogen bond are repelled as the nucleophile approaches the carbon atom. So the arrows are showing the movement of that lone pair of electrons. So that movement of lone pair of electrons from the nucleophile goes to that carbon, and the electrons in the carbon halogen bond are then attracted to just the halogen. That's really important here, that when we're showing the nucleophile coming in, we're showing those electrons going to that carbon, and then we're also showing those electrons from the carbon halogen bond going to the halogen, but from the middle of the bond. We're not showing it from the carbon because we're not taking those electrons from the carbon, we're taking it from the carbon halogen bond, because remember, they're from a covalent pairing. One was from the carbon, one was from the halogen. Okay. When that happens, the nucleophile bonds to the carbon. So basically it's going to replace that halogen. So the carbon halogen bond breaks, the nucleophile bonds to the carbon. The two electrons then move to the halogen, and we then get a halide ion formed. So we obviously need to show that lone pair of electrons on our halide ion and show our charge on our ion as well. The halide is substituted. So this is a nucleophilic substitution reaction. So we're going to look at it for sodium hydroxide. So nucleophilic substitution reactions involving halogenoalkanes are really, really important in the production of other useful molecules. So this is for making other things that are useful that we want. So the reaction of a halogenoalkane with sodium hydroxide. So when we react them with hydroxide. So when halogenoalkanes react with aqueous solutions of sodium hydroxide or potassium hydroxide when warmed. And again, really important on these questions that we're stating on answers that it's an aqueous solution of sodium hydroxide or potassium hydroxide. So let's go through this now. So reactions of halogenoalkanes with hydroxides. So we have a negatively charged hydroxide ion here. So that's our negatively charged hydroxide ion. And it is going to be attracted to the small positive charge on that carbon atom here. Now we're going to show it in display form structure here. Change that so we can see it. So this is the reaction that's going to take place basically. We've got our halogenoalkane, we've got our sodium whatever hydroxide it is reacting, and then this is what we start to form. So here is our halogen, or our halogenoalkane, and here is our nucleophile, in this situation, hydroxide ion. That hydroxide ion is going to be attracted to that carbon that has the bond between that and the halogen. Oops. Then what's going to happen is the electron pair on the hydroxide is going to be donated into the carbon atom. And what happens is, because we have an increased electron density on that carbon, we've only got 2 extra electrons, we can break that covalent bond. And so it causes the electrons in the carbon-bromine bond to be repelled to the bromine. So let's have a look what that looks like. So those electrons are from the hydroxide ion are attracted to the carbon. We've now got an electron density around here. So the electrons that are shared between carbon and bromine are repelled towards the bromine. Finally, the result of this is a formation of a covalent bond between carbon and oxygen, creating an alcohol. And the carbon-bromine bond is simultaneously broken, and that then forms a bromine ion. This process is called hydrolysis. And that's what happens when it's a hydroxide ion, and that will be hydrolysis. And we're going to make an alcohol and then whatever halide. So halogenoalkanes with cyanide. These need to be hot. It's going to be sodium cyanide or potassium cyanide. What you'll notice is actually this reaction is going to look pretty much the same as the one we've just described. So reaction of halogen with cyanide, same thing's going to happen. Our negatively charged cyanide ion is going to be attracted to that positively charged carbon atom. When that happens, the electron pair on the cyanide ion is donated to the carbon. Because now we've got an increase in electron density around the carbon atom, the electrons that are shared between the carbon-bromine bond are then donated, repelled from that bond to the bromine. Finally, we have a formation of a covalent bond between the cyanide and the carbon. And simultaneously, the bond between the carbon and the bromine is broken. Bromine takes that lone pair of electrons with it, and it becomes a bromide ion. So we then form a nitrile and a bromide ion, a halide ion over there. And then finally, the reaction of halogenoalkanes with ammonia. Halogenoalkanes react with excess ammonia. Excess is really important, and it needs to be warmed, and it needs to be in a sealed container. So you're going to see pretty much the same thing again. When the lone The lone pair on the ammonia causes it to be, oh, what have I done? Here we go. So the lone pair on the ammonia molecule is attracted to the small positive charge on the carbon atom in our halogenoalkane. The electron pair on the ammonia is donated to our carbon atom. Here, like we've done before, because we've now got that increase in electron density, the electrons in the carbon-bromine bond are going to be repelled towards the bromine. What's going to happen is this was going to result in the formation of a covalent bond like we've had before between our carbon and the nitrogen in the ammonia. The carbon-bromine bond is simultaneously broken and we form a bromide ion. So here we go. We've got the donation of those electrons. Those electrons have been repelled over to the bromine. Bond breaks, covalent bond forms, and we've now got our bromide ion. So next part. Because we've still got a slightly positive charge here on that nitrogen that's bonded with a carbon. So this is where this is a little bit more complicated. So the lone pair now of another ammonia molecule is going to attack one of the hydrogens attached to the nitrogen. So here we've got that lone pair here of another ammonia molecule. It's going to attack one of the hydrogens attached to the nitrogen. Choosing this one at a minute. That's going to result in the pair of electrons in the nitrogen-hydrogen bond moving onto the nitrogen. What this will do is result in the formation of an amine. So amines themselves are nucleophiles. So that bond's broken. Oops. Right, so here we go. So that bond breaks. Oh, can't pause it. Bond breaks there. The bond breaks between the nitrogen and the hydrogen here and forms between the hydrogen and the nitrogen on the other ammonia molecule. This results in the formation of an amine. Amines are nucleophiles, so then they may attack and further substitute the halogenoalkane, and then that can obviously keep going on and on and on. So the rate of a nucleophilic substitution reaction depends on the strength of a carbon-halogen bond rather than the degree of polarization in the bond. So a carbon-fluorine bond is the strongest, and our carbon-iodine bond is the weakest. Carbon-iodine bond is the weakest, and so it most readily undergoes nucleophilic substitution because it's easier to break that bond. The rate of reactions involving iodoalkanes are the highest. So let's have a go at answering these questions. So nucleophiles are ions or molecules that are electron pair donors. So they're going to donate electrons. They form new covalent bonds. So nucleophiles turn up, they donate electrons, and when they donate those electrons, they form new covalent bonds. Nucleophiles are attracted to the small positive charge on atoms involved in polar bonds. So those atoms are involved in molecules that have polar bonds, and those nucleophiles, which have that lone pair, because of that lone pair, it causes them to have a slightly negative charge. It means they are then attracted to the small positive charge on the atoms. Which ones undergo nucleophilic substitution faster than the other halogenoalkanes? That is iodoalkanes. They have that lowest bond energy to break. Halogenoalkanes react with an ammonia solution to form amines. potassium cyanide to form nitriles, and an aqueous solution of sodium hydroxide to form alcohols. There we go. So, last little bit before we go through some exam questions. I say this, but I can't get this to close. Here we go. Elimination reactions. And we're going to look at what conditions favour substitution, which we've just done, and which conditions favour elimination. So, in a reaction with a strong base, halogenoalkanes will not only undergo not only nucleophilic substitution, but they can also go through elimination reactions. And in elimination reactions, they form alkenes, which have a double bond, and they form water. So here's an example. We've got this nucleophilic substitution going on because we've got that hydroxide ion here. But you can see we've got a double bond formed here, which means we've got our alkane, we've got our water forming there, and we've still got our halide ion. So we've got an elimination reaction occurring as well. In this situation, the hydroxide acts as both a base and a nucleophile. So hydroxides can act as a base and they can act as a nucleophile. When it acts as a base, the hydroxide ion removes a hydrogen ion from the halogenoalkane, which also results in the formation of a halide ion. The reaction between a halogenoalkane and a strong base usually results in the formation of a mixture of substitution and elimination products. So what we're going to have a look at is the elimination between a chloroalkane, so an hydrocarbon that contains chlorine, and hydroxide. So halogenoalkanes react with hot ethanoic acid solutions of sodium hydroxide or potassium hydroxide, which is what we've already talked about. So in this situation, we've got the lone pair on our base, because remember, whilst it is a nucleophile, in this situation, our hydroxide ion is acting as a base. So the lone pair on our base, here we go, we've got our hydroxide ion here, that lone pair is acting as a base in this situation, and it is going to attack one of the hydrogen atoms on a carbon adjacent to the carbon with the halogen. Okay, so this is our carbon that has the halogen, so it's going to attack one of the hydrogens that are attached to the carbon that's adjacent to the carbon that's got the chlorine. So it's going to be that hydrogen or that hydrogen. I'm going to go to the bottom one. So it's going to attack that hydrogen. The electrons in the carbon-hydrogen bond, the electrons in this carbon-hydrogen bond here are pushed into the carbon-carbon bond. It does that because obviously it's attacked here, those electrons are going to go here, so then these electrons are going to go there, and that forms a double bond. And the electrons in the carbon-chlorine bond are repelled onto the chlorine, so that is still occurring as well. So the resulting products of the reaction are an alkene, a chloride ion, and a water molecule. So like we said, when we do elimination, we get a mixture of products. If our carbon chain is 4 or more carbons in length and our halogen is not attached to a terminal carbon, we may get a mixture of positional isomers being formed. So like we said, when we're synthesizing halogenoalkanes, we can often get isomers. When we are going through elimination reactions, if our carbon chain is 4 or more carbons in length and our halogen is not on the terminal carbon, we may get a mixture of positional isomers being formed. So it all depends on where the hydroxide ion is going to attack. If the hydroxide ion comes in and attacks at A, this is what will happen when we get but2-ene. If it attacks at B, we will get but1-ene forming. The conditions for reaction that favour substitution or elimination are different from each other. So base strength. So the stronger the base, the more elimination is favoured. So for example, sodium hydroxide in aqueous solution contains OH minus, so a hydroxide. But when dissolved in ethanol, CH3CH2O negative is also present, and that is a stronger base. So sodium hydroxide, when it's in ethanol, is really important to remember that creates a stronger base than when it's just in an aqueous solution. Therefore, elimination is favoured by sodium hydroxide in ethanolic solution, and substitution is favoured by sodium hydroxide in aqueous solution. This is why earlier when we were talking about substitution reactions, I said it's really important to say that it happens in sodium hydroxide in an aqueous solution, and that's why. Temperature also affects this. Elimination is favoured by hotter temperatures, whereas substitution is favoured by warm conditions. So basically a lower temperature, but not a cold temperature, which is why we're still saying warm conditions. So other thing that can affect it is primary, tertiary, or secondary. So primary halogenoalkanes favour substitution, whereas our tertiary halogenoalkanes favour elimination. If it's in the middle, it doesn't really make much of a difference. So primary, substitution more likely. Tertiary, elimination more likely. Secondary, could be anything. So let's have a look at these. Substitution or elimination. We're in a warm aqueous solution of sodium hydroxide. Well, that is going to be more likely to be a nucleophilic substitution because we're in a warm aqueous sodium hydroxide. Substitution or elimination in hot sodium hydroxide in ethanol. Well, that is going to be more likely to be elimination. Actually, let's look at the structure of this as well. We've also got a tertiary halogenoalkane going on there, which favours elimination as well. There we go. In warm aqueous sodium hydroxide, probably going to be substitution. Let's have another look as well. Well, let's look at this. This is only a primary one. So yeah, nucleophilic substitution. In warm aqueous sodium hydroxide, whilst it is tertiary, 1, 2, 3, we're in warm aqueous sodium hydroxide, so it's still going to be nucleophilic substitution. Oh, no, it's not. It's going to be elimination because it's tertiary. In hot sodium hydroxide in ethanol, we are going to have elimination. And that is the end. So let's quickly recap. Nucleophilic substitution, as we said, halogens have a greater electronegativity than the carbon they're bonded with. Electronegativity, the definition of that is the ability to attract that shared pair in a covalent bond. So we get an induced dipole in the carbon halogen bond and it becomes polar. The carbon is then open to attacks by nucleophiles, and obviously we know nucleophile means liking positive. So the greater electronegativity of a halogen attracts the shared pair of electrons, so it becomes slightly negative. The bond becomes polar. Nucleophiles, also known as electron pair donors, they have at least one lone pair of electrons. They don't have to have a negative charge. They are attracted to slightly positive carbon. Examples are hydroxides, cyanides, ammonias, and water, but water is a poor nucleophile, so we often don't use that. So nucleophilic substitution. What happens is our nucleophile comes along, it uses its lone pair to provide the electrons for a new bond. Our halogen is going to be displaced, and that's just because carbon can only have 8 electrons in its outer shell. And the result is substitution following attack by a nucleophile. The mechanism is therefore known as nucleophilic substitution. Really important things here. Our nucleophile has a lone pair of electrons. Our carbon-halogen bond is polar. Curly arrows need to be drawn from the lone pair to the slightly positive carbon here, like that. And a curly arrow is used to show the movement of the pair of electrons here, and it needs to go from that bond to the halogen. Carbon is restricted to 8 electrons in its outer shell. Therefore, we must break a bond. Our polar carbon-halogen bond breaks heterolytically, and that means it's broken unevenly. So that means that those lone pair of electrons, those 2 electrons have gone with the halogen, so that's an uneven breakage. That second curly arrow shows the shared pair moving onto the halogen. Because that bond breaks, they move there. Halogen now has its own electron back, plus that from the carbon atom. It now becomes a negatively charged halide ion, and that's because one of those electrons was originally from the carbon. And the halide ion is displaced. Here we go. Nucleophile comes in and attacks. And we form a halide ion. Rate of reaction happens depending on how much it takes to break bonds. Carbon iodine have the lowest bond energy, so they're the weakest, they're the easiest to break, so their rate of reaction is a lot higher than halogens that have a carbon fluorine bond. An experiment you can use with this is we can look at different nucleophiles and how they displace halides. So you could use water. We've said water is a poor nucleophile, but it can slowly displace halide ions. So if we had aqueous silver nitrate and we shake it with a haloalkane, the displaced halide combines with a silver ion and it forms a precipitate of silver halide. The weaker the carbon halogen bond, the quicker the precipitate appears. So that's something that you could do. So this is just a quick overview of nucleophilic substitution of aqueous sodium hydroxide. Aqueous, really, really, really important. You need to quote the solvent when answering these questions. So when we say nucleophilic substitution happens, you need to say it happens in aqueous sodium or potassium hydroxide. And that's because when we're talking about elimination, we're obviously using those hydroxide ions, but that takes place with ethanol being the solvent, and you need to know the difference. You need to know, well, hang on, is this elimination? What solvent does elimination take place in as opposed to substitution? So that's really important. Conditions: it needs to be in reflux in aqueous solution, makes an alcohol and a hydroxide ion. So our mechanism, exactly the same as we've talked about before. So we go from our halogenoalkane, our sodium hydroxide aqueous solution, and then obviously we get our alcohol here, and then our hydroxide ion. Potassium cyanide. It's going to be an aqueous alcoholic potassium cyanide or sodium cyanide. Reflux in aqueous or alcoholic solution can be either. We're going to make a nitrile at the end and then a cyanide ion. What's really important is it can extend the carbon chain by 1 carbon atom, and the cyanide group can be converted to carboxylic acids or amines later, but we'll look at that later. And then finally, ammonia needs to be in excess. This is our important bit. Solvent can be aqueous or alcoholic, but it needs to be in excess and it needs to be under pressure. Ammonias produce amines and then an ammonia amines. So this equation shows 2 ammonia molecules. The second one ensures that a salt is not formed. So that's really important here. So don't need to do that in a minute. Don't worry about elimination versus substitution. So the products of reactions between haloalkanes and hydroxides are influenced by the solvent. So water, if the solvent is water, hydroxide ion is going to be working as a nucleophile. Mechanism is going to be substitution. The product is going to be alcohol. If the hydroxide ion is in alcohol, the hydroxide ion is going to be acting as a base. It's going to go through elimination and the product is going to be an alkene and water. So in aqueous solution, our hydroxide ion is going to attack the slightly positive carbon bonded to the halogen. So our hydroxide ion acts as a nucleophile. Alcoholic solution, our hydroxide ion attacks one of the hydrogen atoms on a carbon atom adjacent, and the carbon bonded to the halogen. So our hydroxide ion acts as a base in this situation here. Both reactions take place at the same time, but by varying solvent, you can influence which mechanism dominates. So elimination. Quick overview of that. Alcoholic, really important. Sodium or potassium hydroxide, we're going to make an alkene. And obviously this one is where it works a little bit differently. So our hydroxide ion this time is going to act as a base, and it picks up a proton in this situation, okay? What's going to happen is this proton comes from a carbon atom next to that bonded to the halogen. So this is where we focus on this bit here. The electron pair left moves to form a second bond between the carbon atoms, and the halogen is then displaced. So overall, there is an elimination of hydrogen bromide. With unsymmetrical haloalkanes, you can get a mixture of products being formed as well. Going to look at those in a minute. So let's have a quick look at a couple of these exam questions which I've got on here. Oh no. Why has it done this? No. Ah, there they are. So these are some exam questions from AQA looking at halogenoalkanes. So a 1-mark question, it's a really important question actually to make sure we know what's happening. Which of the arrows labelled A, B, C or D, the mechanism in the diagram is not correct? It seems quite an easy question, and it is, but it's assuming a lot of knowledge. It's not telling us what the mechanism is. So you need to look at this and know what the mechanism is that's going on. Obviously here, at the beginning, we've got that ammonia nucleophile coming in. So let's have a look at these arrows and how they're working in, if they're looking right. So ammonia is coming in. It's attacking carbon. So this is basically like our nucleophilic substitution part. We've got electron density increasing here. So the electrons from the bond between the carbon and the bromine goes from the carbon to the bromine. So yeah, arrow A looks fine, arrow B looks fine. Let's look at C and D. So here, this is when we then get that propagation going on, like we said earlier, when then another ammonia nucleophile can come in and then attack a hydrogen on there. So that ammonia ion comes in, it attacks that hydrogen. Yep, that's fine. The bonds break and those two electrons go to the hydrogen. Well, that's not going to happen because if we count how many, because obviously we've got that slightly positive here. So when we look at that and add all that up, that's not going to happen. And that's not going to happen because obviously that arrow needs to go in this direction. So the issue here is arrow C. So C is the incorrect arrow. So number 2, 2-bromo 2-methylpentane is heated with potassium hydroxide dissolved in ethanol. 2 structural isomers are formed. State the meaning of the term structural isomer. So that's quite a nice question. These questions can be quite long. Oops, did not want to move that. Can be quite long. So yeah, let's have a look here. We'll state the meaning of the term structural isomer. I'll just move that a bit more. Oops. No. Just get rid of the keyboard. I don't know what's happened. Close that. Why is half my screen gone? Oh, that would make more sense. It's now thinking about life. Here we go. Let's try this again. Right, type it in there and move it over. To state the meaning of a term of a structural isomer. Well, a structural isomer, well, they're compounds, so that's the most important thing. We're going to start off with the correct sort of terminology. So they're compounds which have the compounds which have the same molecular formula. So the compounds that have the same molecular formula, we know they have the same molecular formula. They've got all those same atoms inside them. So the compounds which have the same molecular formula, but they have different, and you can choose any of the terms. You can say structural, displayed, or skeletal. I'm going to use structural formula, but you could use any of those 3. So state the meaning of the term structural isomers. It is a compound which has, I've lost my writing. Compounds which have the same molecular formula, but they have different structural formula. That will get you the 1 mark. So the important part is here, same structural formula. And the next important part is different structural formula. So let's look at this now. So it's 2-bromo 2-methylpentane. And this next question is worth 6 marks, I think. Yes. What it wants you to do is it wants you to draw the mechanism for the formation of one of the isomers that could be made. And what's happening is it's being heated with potassium hydroxide dissolved in ethanol. Well, here we go, straight away. We're being told it's being dissolved in ethanol. If it's dissolved in ethanol, that must mean that we are having an elimination mechanism going on. So here it will be elimination. If on the exam you couldn't recall anything else about that other than it's an elimination mechanism, that would get you 1 mark. Oh, no. So the next thing we need to do is now name and draw the mechanism for formation of one of these isomers. So the first thing we need to do then, I'm just going to make this, oops, no, what am I doing? Bring the screen in a little bit less, just so I can see the name. Actually, let me just write it down because then I can see of what we are going to draw. So we're going to draw 2-bromomethyl pentane. We're going to heat it with potassium hydroxide. So first of all, we need to draw out 2-bromomethyl pentane. So pentane, we've got an alkane. Pent means we've got 1, 2, 3, 4, 5.
Excuse me, Rebecca, sorry. I'm not getting in the screen all the thing, like just the plain doodle learn thing is there on the screen.
Ah.
Yeah. So.
Right. Yeah, it didn't swap.
So
sorry.
Oh,
yeah, let me just get back up. So I'll just show you what I've been talking about.
Yeah,
thank you. A minute ago. So yeah, so they're the areas that we were talking about earlier. 1 second. And then structural isomers. And then obviously we've got the elimination reaction that we need to then have a go at drawing. 1 sec. So the elimination reaction, we need to draw out 2-bromo, 2-methyl pentane. So yeah, so we've got the 5 carbons in pentane that we need to draw first of all. So let's get them on first. So we've got carbon, 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 carbon. 2-bromo. So if we number our carbons, we've got 1, 2, 3, 4, 5. That means our bromine is going to be attached to that second carbon. So 2-bromo, so I'm going to pop it up here. So 2-bromo, 2-methyl pentane, and that also means we've got a methyl group on our second carbon. So we'll add that on down here. And then obviously the only thing we have left to do now is add all our hydrogens on. Make sure you do add all your hydrogens on when you're answering these questions. It's really important because when we're showing the elimination, obviously it's going to involve us using the hydrogens. So yeah, that's important to add on. Here we go. So we've got 2-bromo, 2-methyl pentane drawn on. Let's add on our potassium hydroxide ion. We don't need to actually show it as potassium hydroxide. We can literally just show it as a hydroxide ion. So I'm going to draw that just in different colour just for the sake of making it clear that it's our hydroxide nucleophile. That is going to come in here. H. Oh. HO negative, and we've got our 2 electrons on it, lone pair. So first thing we need to do, again, I'm just going to keep using different colours so we can see it nice and clear, is we're going to show where that attraction is going to happen with that hydroxide ion, where it's going to attract. Now it could attack in 2 different places, because if you remember in eliminations, they attack one of the hydrogens attached to the carbon that is adjacent to the carbon that the halogen is attached to. So basically it could attack any of the hydrogens attached to carbon 1 or any of the hydrogens attached to carbon 2. I'm going to show it attacking this hydrogen here, But actually, I'm going to try. Just going to do something sneaky. So then I can show it you the other way around as well. So I can show you both isomers in a minute without me having to draw the whole thing out. So here we go. It's going to attack this hydrogen. Curly arrow, remember it needs to be curly, full arrow ahead. Going to attack there. What then happens is because we've then got a full amount of electrons, full shell on that hydrogen, the bond between the carbon and hydrogen is going to break, and those electrons are going to go from here to here. Oops, no, we're not going to do that. We're going to go from here to here. Then, like we've done before, we still have that substitution going on. So that carbon bromine bond is going to break, and the electrons from that carbon bromine bond are going to go from that bond all up to the bromine. Okay. What we then form would be this. Now it only asks us to show the name and draw the mechanism for formation of one of the isomers. We actually need to show one of the isomers that's formed at the end. We don't also have to show the bromide ion, and we don't need to show the water either. So then we just need to show the isomer. So then what would form from this is obviously here at the carbon and the carbon, we're going to get that double bond forming here. So we'll have carbon, carbon double bond, and we'll obviously have the two hydrogens coming off it, because obviously this hydrogen's lost now. It goes with off with the hydroxide ion, so that's going to break off. And so we've got hydrogen here. We've got the double bond. Obviously that bromine has gone now as well to become bromide ion. So actually we can show the rest of all of this section here as a branch. So if we branch that off, so that would then be CH2 for this part, CH2 for that one. Why it does that? CH2 for that one, and then the last part, CH3. And then branching off the bottom, we just obviously have our methyl groups down there, CH3. Quickly just going to show you at the side what would happen if our hydroxide, potassium hydroxide, attacked at a different position, and what isomer would make them. Here we go. Add on our potassium hydroxide again, OH minus lone electron pairs. Exactly the same thing's going to happen, but I didn't want to draw it there, which doesn't help the situation. Here we go. I'm going to draw it down here this time, because we're going to attack at the third carbon. So this time, electrons are going to go to this hydrogen. It would help if my arrow was drawn a bit better, which means that from that hydrogen, we're going to have the electrons go into that bond here. So then from that bond there, we've got an increase in the density of electrons, which then will mean from the carbon and the bromine, that's going to break there. So it's just that those arrows are going to come in at a different location, otherwise exactly the same. So then the isomer that will be formed this time will obviously be different, because obviously we've got a different hydrogen being eliminated in this process. So we've got our carbon-carbon double bond here that I'm going to draw first. It's between carbon 2 and 3. So carbon 2 and carbon 3 are going to have that double bond. So carbon 1 is just going to come off up the top as CH3 as a methyl group. We've obviously got that methyl group as well still attached to carbon 2. That's going to come off here as CH3. Then carbon 3 is just going to have one hydrogen attached to it, because this one's gone at the top. And then it's going to have this part here. So it will still have, oops, it's a H, CH2 and CH3. So that's the other isomer that we could form. So that's what we sort of mean by those questions there. What we will do tomorrow is we will have the last tiny bit of halogens, because we just need to look at what they're used for. So CFCs and the ozone layer and how they can affect the ozone layer. Have another quick look at a couple of exam questions, and then we will go on to alkenes. So I will leave it there for that. Tomorrow